This is a recorded version of a talk presented at SIGMOD 2024. My name is Wolfgang Gatterbauer and this joint work with Coditan. Our main motivation with this work is to help humans understand relational queries faster. So why would we ever care about that? Let's look at 3 use cases. First case. Assume you're issuing a query to a voice assistant and you would like to verify that the voice assistant understood and interpreted your query correctly. Second case. Assume you're teaching a database class and you are asking the students to write a query for each beer that Eve likes, find bars serving it at the highest price. I've taken this example from Jun Young's keynote at the data ad workshop just before SIGMOD. Here on the left, we see a correct query. Here on the right, we see an incorrect query that a student issued. And the student now would like to understand from you why it is wrong. It turns out that the query on the right finds bars not serving it at the lowest price. By now we know what these 2 queries are returning, but I would still not find it trivial to explain to the student how these queries exactly do what they do. Third case. Assume we are trying to write a query ourselves. We want to find students who have taken all classes in the art department. Now imagine that instead of starting from scratch, we could browse through a repository of example queries. And while we're browsing, we find a query that asks for sailors who reserved all red boats. So this query that we're looking at right now seems in some imprecise way to use a similar pattern as the query we want to write. Wouldn't it be easy to write our own query by starting from this query with a similar pattern? So in all of the 3 examples, we could benefit from a service that helps us understand existing queries, whether we speak a query, or somebody else writes the query, or we write the query ourselves. What I'd like you to notice is that we do not just want to understand what the query does, but also how it does it. And with how, I don't mean the join order or query execution plan, but rather how the individual parts of a query expression relate to each other, how they together express the query's intent, the meaning of the query. And this is what we refer to as the relational pattern of a query. Our 4 contributions in this paper. We first give a semantic and language independent definition of relational query patterns. We then use this definition to compare the relative pattern expressiveness of relational languages. Interestingly, we show that calculus can express certain patterns that algebra cannot. We present a rather natural diagrammatic representation of safe two-positional calculus. And we present a user study in which the participants were not only faster and more accurate in understanding queries with our representation than with SQL, but they were also still learning. That means they were still getting faster as they progressed through the exercises in our study. We start with relational diagrams. Relational diagrams are an unambiguous, relational complete diagrammatic representation of safe two-positional calculus. For queries without disjunctions, the translation is really straightforward, as we will see in a moment. Whenever we have disjunctions, then we first need to translate the query into a union of disjunction-free queries. And while our translation normally starts from relational calculus, we will illustrate here with SQL instead, just because more people are familiar with SQL. Here we have a complicated enough query on the left, and we will translate it into the representation on the right in 5 steps. First step, we look at the nested negation scopes in the query. Whenever we have negation, then it applies to a certain subset of the query. So negation has a certain scope. And in any query, these negation scopes form, by definition, a hierarchy. This hierarchical nesting very naturally translates into a hierarchical partitioning of the canvas, which we show with nested dashed rounded rectangles. Here the innermost scope, let's call this Q2, is nested inside of Q1, and Q1 is nested in Q0, which is everything outside any negation scope. Second step, we look at the tables that are quantified in various scopes, and we place their names into the appropriate partitions of the canvas. Notice that in SQL and two-positional calculus, we have to use table variables and aliases, like S1 and S2, to be able to disambiguate which occurrence we mean in a particular predicate. But we do not need this interaction in a diagrammatic representation, because we'll just place attributes adjacent to their respective tables. Third step, selection predicates. For each selection predicate, we place the attributes below its table in a typical UML notation, and we put the selection into the same box. So here b equals 0. Fourth step, for each join predicate, we place an edge between the attributes and add the comparison operator as label on the edge, except for equijoins. If we have an asymmetric operator, we use a directed edge. And the way we define here the interpretation of a label like smaller than is that the smaller starts at the tail of the edge and the bigger is at the head of the edge. And because the most widely used convention on reading directions are left to right and top down, we respect these conventions by appropriately orienting edges and labels. Fifth step, if we have a non-Boolean query, then we place an output table that we call Q for query result in the outer partition Q0, and we add the appropriate edges. Finally, if we have a union of disjunction-free queries, then we just place each of the disjunction-free queries into a separate cell. We refer to them as union cells and interpret the semantics very similar to Datalog, where one specifies different rules with the same header for a union of disjunction-free queries. In summary, relational diagrams allow a pretty natural translation from tuple relational calculus, we just illustrated here with SQL. We start from a very familiar UML notation for conjunctive queries. We represent the negation scopes with hierarchically nested dashed rectangles and disjunctions with union cells. So we've asked the famous mathematician Martin Gardner to comment on our diagrams, and he stated in his book, after you work with the diagrams for a while, the patterns are soon memorized. So that is not true. He did make this comment, just not on relational diagrams, but about Venn diagrams. But we did get a similar statement from an anonymous participant in our user study who left the following comment. At first, I didn't get it, but after staring at the diagrams for a few minutes, it clicked and everything became super simple. I saw the patterns. So this is exactly what we were hoping to achieve with our representation. We next give our definition of relational patterns. We illustrate the definition here with a Datalog query for relational division. The definition needs 3 steps. First step, we only focus on the extensional items of a query. Every relational language needs to reference the database tables in whatever language-specific way. Our query here references the table R 3 times and the table S only 1 time. Next, we treat each of the multiple occurrences of the R table as separate. We say that we dissociate the tables and call the result the dissociated query. So now the signature of this dissociated query has 4 different tables, R1, R2, R3, and S. And finally, we are focusing on the logical function that is defined by this dissociated query. We say function because every query maps the input, in this case 4 different tables, to an output, and that defines a logical function. So our definition of the relational pattern of a query is the logical function represented by the dissociated query. Let's now use the definition to verify whether these 3 queries on the left use the same pattern. That means whether they are pattern equivalent. Notice first that they use 3 very different languages. Datalog is usually called declarative, we have relational algebra, usually called procedural, and we have a diagrammatic representation. Yet they are logically equivalent. That means they express the same logical function before dissociation. So let's apply the definition. We focus only on the extensional atoms. These may be represented in different ways in different languages, but every relational language needs to reference the input tables. We dissociate the queries. That means we treat each of the tables as distinct. And then we are trying to see whether there is some mapping between these dissociated tables across the queries that preserves logical equivalence of these expressions. That means they continue to express the same logical function. Here we found it, and thus these 3 queries are not just logic equivalent, but they're also pattern equivalent. Now, what about queries using different schemas? Well, queries between different schemas can't be logically equivalent but they can still use what we call similar patterns. Let's illustrate this for this query. Find sailors reserved all boats. Here is the representation as relational algebra. I'd like you to notice that this relational algebra expression uses 3 different tables, and it uses the sailor table twice. But the left 3 queries use only 2 different tables and repeat the R table 3 times. So these queries not only use different schemas, they even repeat tables a different number of times. Let's first visualize the query on the right as relational diagram. Now you can, or maybe can already see intuitively that somehow these 2 queries use a similar pattern. Topologically, they look very similar if you ignore the names and constants. And this intuition can be made more formal. If you first dissociate the tables on both sides, so we have 4 different tables in each query, and then also rename those tables and the attributes and a constant that appear, then the dissociated query on the left actually expresses the same logical function as the one on the right. That means if you insert exactly the same tuples into the left 4 tables as the right 4 tables, then both queries will return the same output. So while our originally non-dissociated queries were not logically equivalent and thus neither pattern equivalent, we can say that they use a similar relational query pattern. And there's another reason why we use dissociation in our definition of relational patterns, not just for pattern similarity, but also for pattern equivalence. I'm showing you here 2 queries that are logically equivalent in Datalog, in SQL, and as relational diagrams. Yet while the left and the right queries are logically equivalent, you probably already see that they are using somewhat different patterns. The joins are between different attributes. And in some languages, the tables on the left don't even need to be binary. Our definition takes care of this because after you dissociate the tables, the left and the right queries are not logically equivalent anymore. So here's an example. And that's exactly what we wanted to achieve with our definition. The original queries are logically equivalent, but they are not pattern equivalent because the dissociated queries are not logically equivalent anymore. So to summarize, relational patterns are defined semantically, irrespective of the syntax of an individual query language, whether declarative, procedural, or diagrammatic. We define patterns solely on the extensional database relations used in the queries. Logically equivalent queries may or may not be pattern equivalent, and queries across different schemas may be pattern similar, although they can never be logically equivalent. We next compare the pattern expressiveness of different relational languages. We see here the query find sailors who reserved all boats in SQL. What we show in our paper is that this SQL query has no pattern equivalent representation in relational algebra. Now we know that there must be a logically equivalent query. After all, relational algebra is relationally complete. However, there is no relational algebra expression with the basic 5 algebraic operators that expresses that query with the same relational pattern. Relational algebra needs to use the Sailor relation twice, even if you throw in an operator for the antijoin. And thus, relational algebra uses a different relational signature and thus relational pattern. Here's how relational diagrams represent these 2 queries. Let's now try to read these patterns. On the left, find sailors such that there doesn't exist any boat that is not reserved by that sailor. This is a pattern that cannot be represented in relational algebra. Instead, relational algebra represents this as follows. Find sailors such that there doesn't exist any product between the sailor and the boat that is not contained in the reserves table. These 2 are logically equivalent, but they're using different table signatures and thus also different patterns. Thus, calculus can express relational patterns that cannot be expressed in algebra. This is also interesting because there's been a lot of work on visual query languages, and the majority of these languages work by mapping the operators of relational algebra to some visual representation. So the way this normally works is that you take a relational algebra expression, you look at the abstract syntax tree, and then you give them some visual representation. Here's an example called data flow from 40 years ago. So what our lemma in this paper implies is that any visual language that is a direct visualization of relational algebra operators is not able to represent the pattern used for this very query on the left. You'll always run into the problem that the visual representation will show you two scalar relations. And is the visualization on the right then really helping us understand the query on the left, its logic, the intuition of its relational pattern? Let's have a quick look at our exciting user study. Our study shows that participants are more accurate and faster in understanding queries by using relational diagrams instead of SQL, and the participants are still getting faster while they participate in the study. For that to show, we use a counterbalance within subject study that I'm very excited about and that we had thought about quite a bit. Notably, our setup allows us to measure learning by comparing the performance of participants during the first and the second half of the runs. We have monetary incentives for correctness and speed. The setup is fully scalable. Thus, if we had more money, we would get more data, but there would be no extra analysis work. The mental work was all done before we gathered the data. We have fully parameterized the questions with a combinatorial number of possible treatments that guarantees with very high probability that no two participants ever get the same treatment. This setup allows us to prevent cheating via leaked solutions. And very important, our study was pre-registered before we collected any data. So we specified exactly what we are going to do, including the very Python notebook for the analysis. And once we gathered the data, we just executed the notebook on the data and out came the figures. Some open issues not addressed by our work. First, is it possible to create diagrammatic representations that are also pattern preserving for arbitrary disjunctions? So we could avoid having to rewrite a query as a union of disjunction-free queries. It turns out that this is a complicated problem, and we are not the first ones to observe it. Second, can one overcome the reduced pattern expressiveness of algebra by just adding more operators? We believe there is a fundamental difference between calculus and algebra, and any finite addition of operators will not overcome this separation. Third, how can we represent arbitrary groupings and aggregates? Fourth, can we create an easy-to-use implementation? I know there's a lot of demand for this, and users would like to just copy and paste the queries into an interface, very similar to the interface we had created years ago for QueryWiz. And finally, there's a lot of excitement in our community in natural language interfaces to databases. And natural language is here to stay, especially as informal, fast way to specify what one wants. But SQL is likely to stay as the language that databases speak. So what is the right way for an assistant to talk back to the user? When it matters and we want to be precise, then the inherent ambiguity in natural language may not be the right way. And as we have shown, diagrammatic representations can be unambiguous and can help humans understand queries faster and more accurately than text, even after only a very brief exposure. So we believe they will play a more important role, in human-computer interactions in the near future. Thank you for your attention.